As I've said a couple of times already, turbulence is always unsteady and three-dimensional, which makes it difficult to do things like think about what's really happening with the flow. I mean, if the flow is going in all the different directions and it's changing every single moment, so how do you say things like flow is traveling down the pipe? I mean, how do you define velocity in that context? And if you have flow over a plate, how can you? It is generally traveling, say, from left to right. But if the flow is swirling and spinning, looking at the velocity at a particular point won't necessarily reveal that. So people have gotten into the habit, both for modeling purposes and just for thinking about turbulence, of using time average velocity equations and time average properties. So what does that mean? So that means that the velocity, which is actually, such as u, which is actually swirling and changing at every point in the turbulent flow, it's changing at every moment. But on average, it might be going from left to right. And so we break that velocity into two components. I'm putting a tilde over the top here to indicate an average velocity and a prime to indicate the time-dependent perturbation. So there might be an average velocity of 3 meters per second from left to right, but at any given moment, that velocity could be changing forwards and backwards, up and down, etc. And so we can think of the velocity as having those two components: its average component plus its time-dependent turbulent component. So that's a way of helping us to get some sort of meaningful information and talk about turbulent flow in a more understandable way than just saying, well, it's always changing and you really can't say anything about it. So we're going to, if you do that, you can turn the equations into time averaged equations. The equations we're familiar with, the Navier-Stokes equations. So if we're looking at, I'm going to put this in quotes, steady turbulent flow, if it's really a two-dimensional problem, one where the average components are non-zero only in two dimensions, such as flow over a plate would be an example of that. There would be third-dimensional effects as turbulence swirls in the z direction and then out of the paper, but that's going to average to zero. So that's not going to have it. There's not going to be an average component that is non-zero in that third dimension. And if you do that, you can arrive at the equations of motion that we have, the Navier-Stokes equations. So that's your mass conservation. So that's completely unchanged. It looks just like the regular two-dimensional mass conservation equation in U and V. That's supposed to be a V, sorry. U dV tilde dy. So that's exactly like the one that we had before. The momentum equations do not stay exactly the same. So they look pretty similar. Certainly this part looks familiar, hopefully to you by this point. So we have u du dv. Oh, God, I'm writing terribly today. U du dx, v du dy, and then minus is equal to minus 1 over rho dp dx. So that's an average pressure now, because the pressure also can fluctuate as a result of turbulent motion. But the last term, the viscosity terms, do not look the same. So we're going to have d by dx nu plus something called epsilon m. So this is a new thing here, du dx. And then finally, d by dy of nu plus epsilon m du dy. So these terms do not look the same. That's the tilde. That's a nu, not nu squared. It's just nu. These terms do not look the same here at the end. This nu plus epsilon m and this nu plus epsilon m here. And you have that same thing, and that's the x momentum equation. And you have that same thing in the y momentum equation. So in the y momentum equation, you also have the same side of same form on the left that you would have for the non-time averaged equation. So again, here's the y momentum equation. So again, the left-hand side basically the same as it would be if you have non-time averaging, just as it was with the x momentum equation. We still have a pressure term with now the time average fluctuating pressure, but we have this additional epsilon m appearing in the viscosity terms. So the viscosity term here is different. Note that this term, for instance, this term would take the form as we've written in the past as nu d squared v dy squared. That would be for the non-time average term. So two things have changed. One is we've got this nu inside this derivative here. It's still a second derivative, though we're leaving open the possibility that nu plus epsilon m might be a function of y, and that's because epsilon m might be a function of y. So we can't pull this out of this derivative. It's got to stay inside. This form of the equation assumes that nu is constant in space, which is usually a very good approximation or assumption. But in the case of turbulence, it may not be. Epsilon m, as I've said, has a name. Epsilon m is momentum eddy, E-D-D-Y, diffusivity. So that's the momentum eddy diffusivity. And there are lots of different models for it. So this thing gets modeled. All the models are based on experiments. There's no theoretical basis for turbulent modeling, really. There's some theoretical underpinnings, but no rigorous theoretical understanding of turbulence for this kind of model. But people have come up with different models to try to come up with values for epsilon m, and ultimately they all rely on experiments. What epsilon m functionally does, of course, is it increases viscosity. So wherever you see this viscosity term here and here and here and here, everywhere there's a viscosity, epsilon m is actually increasing that viscosity. So as we've said before, turbulence increases friction. It increases friction. And so we're seeing that very directly in this way of modeling these equations. If you look at these time average equations, very clearly the fact that epsilon m is non-zero for turbulent flow means you're going to have effectively a larger viscosity. So again, epsilon m, it may be a function of both x and y and z. It can be spatially varying, so it's not a constant necessarily in space. And it increases friction. If you want to come up with the shear stress, it's called the apparent shear stress when you're dealing with turbulence. And that would be rho times nu plus epsilon m times du dy, if of course you were talking about this is normal to the surface. So if you're talking about a plate, for instance, that's aligned in the x direction, so normal to the flow would be in the y direction, then you would use a stress calculation. It includes both nu and epsilon m. Of course, usually again we use mu du dy here, and of course rho times nu is mu, but epsilon m is here because epsilon m functionally increases the shear stress on the wall, the apparent shear stress. And so finally, I'll emphasize again, epsilon m ultimately depends on experimental verification. So there are many models for how you might sort of arrive at an epsilon m, but at the end of the day, every model of this type of turbulence modeling requires that somebody do an experiment and try to come up with some values that actually match real world data, because turbulence modeling is just a very approximate science.